Hello, welcome back all of you. So we'll continue with the concepts of different type of signals that are frequently encountered in the signals and systems as well as communication systems. So I will discuss the next type of signal, that is signum function. Signal function, also written as denoted as SGN argument T, can be defined mathematically as its value is equal to 1 for time greater than 0 and 0 for time equal to 0 and minus 1 for t less than 0. And further, we can also represent a signum function in terms of a unit step function, that is signum t can be written as minus 1 plus 2 times of u of t. If you simplify this right hand side of this expression, minus 1 plus 2 times u of t, you will find that it results effectively into a signum function. The significance of signum function is that it is one of the most often used signals in communication and control theory. So it is frequently used in communication and control theory. And graphically, if we try to plot this function, signum function, it is plus 1 for t greater than 0, that's your time axis, 0 at time t is equal to 0, and minus 1 for t less than 0. This is how we can represent this function graphically. Another important feature of signum function is that it is an odd function of an independent variable time t. It is an odd function. The next frequently used function is the rect function. So the rect function can be defined mathematically as k times of rect t is equal to k for t spanning from minus 1 by 2 to 1 by 2 and 0 otherwise. This is how we can define a rect function mathematically. If we plot this function, this is your k times of rect t. So in general, we can say that if we want to define this rect function in a more general way, we can say that k times of rect t divided by capital T is equal to k for time spanning from minus t by 2 to t by 2 and 0 otherwise. This is how we can define the rect function in a more general way. Further, another important function is sinc function. Sinc function is denoted as sinc t is equal to, it can be defined as sine of pi t divided by pi t. It's again a very important function when we're dealing with communication systems and signaling systems and also control systems. It is an even function. It is an even function. So if we draw it graphically, we look at it graphically, let us plot this function. It is something like this. this is your sync function. This is your time axis t. Some of the important features, if we look at the graph of this function sync t, is that it has the maximum value of 1, which is at time t is equal to 0. That means maximum of sync t is equal to 1, that is at time t is equal to 0. Second important feature that we can extract from this plot is that it is an even function of time t, that is sync minus t is equal to sync t, even function. Further, we can see that the sync function crosses the time axis or has value 0 at integer values. You can clearly see over there it has 0 at integer values of m. That is, you can also see derive it mathematically, that is sine pi t upon pi t, which is nothing but equal to sync t equal to 0. Thus you can say that sine pi t is equal to 0, or we can say pi t is equal to n of pi, where n is any integer value. Plus minus of n of pi, where n is any integer value. It is really very important to look at the relationship between a sync function and a sine function. How do we convert a sync function to a sine function, or a sine function to a sync function? Because it will be frequently used while dealing with some complex problems. So in general, we can see that sync of at is equal to sine of pi at divided by pi at. This is one general expression. And sine of at by pt can be written as in terms of sync function as a by b times of sync at upon pi. There's a very good shortcut trick that we can use to convert a sine function into a sync function. Let us see how. Let's take the same example, that is sine at divided by bt. This is a kind of a general sync function given to us. Now we need to convert it into a sync function. Let us see how we can do that. Just write down sync here first, and first we'll write down the argument of the sync function. Just look at the argument of the sine function. It is at. So just write at divided by pi. Whatever is the argument of the sine function, you have to use the same argument but divided by pi. That is the first step. Second step is to write down the amplitude of this sync function. Alright, that we can easily find out using the same sine function. Just hide the sine part. You're left with what? at by bt, which is equivalent to a by b. So a by b will be the amplitude. So to find out the amplitude, you will just hide the sinusoidal part, and whatever is the left, the argument divided by the denominator, just simplify that, and that will act as the amplitude a by b. And this is how we can easily convert a sine function to a sync function. Okay, so next let us do one numerical problem. So as to how that will give a good idea how to convert given signal, the graph plot of a given signal in the form of mathematical equation. Let's say we have a signal x of t. So this is the given signal x of t, and we need to write down this signal mathematically. So we'll begin with the signal. The signal begins from time t is equal to -1. So if we write down the expression of x of t, we know it is a unit step function, a kind of a shifted unit step function, right? And it is starting from t is equal to -1. So it is what? U of t plus 1, right? So this u of t plus 1 is what? Something like this, starting from -1 to infinity, right? But we need to stop this signal at +1. You can see over here the signal spans till +1. So we need to stop the signal at +1. So what we'll do is we'll subtract this. We'll subtract another unit step function from this function, and that will be again a shifted unit step function. So it will be minus of u of t minus 1, right? So when we subtract these two, we are left with something like this, right? Now the next is we need to add a unit step function whose amplitude is 2, right? And which is shifted to +1. Shifted to +1. We'll add twice of amplitude is 2 because u of t minus 1. So that will give us a unit step function, something like this. +2, right? Now if you look at the required signal, this unit step function with amplitude 2, it stops at point +3. It should finish at point +3, time t is equal to +3, right? So we need to subtract a signal, again a unit step signal whose amplitude is +2 and is shifted to time t is equal to +3. So we'll subtract minus 2 times of u of t minus 3. So that will give us what? Something like this. This is +3 and this is +1 minus 2. Now if you look at the further parts of the signal, required signal, it spans from +3 to +5 and the amplitude is -1. Currently we are at this point. We need to invert this signal. That means we need to further subtract the signal. So if we are at this point, we subtracted this unit step signal. So we are at this point. So further we need an inverted unit step signal which is shifted at time t is equal to +3. So what we'll do is the amplitude will be -1 times of u of t minus 3. That will give us a unit step function, something like this. Okay. Further, if we look at the desired signal, it stops at time t is equal to +5. That means we need to limit this signal at this. That means we'll subtract another inverted signal which is shifted to +5. We'll subtract another inverted signal with amplitude -1 and shifted to -5. So this is the mathematical expression of this signal. This is how we can step by step write down any signal mathematically. We can further simplify it by simplifying these mathematical operations. But this is the way how do we represent any given signal, any graphical given signal into mathematical expression. Similarly, let us look at one more problem over here, where we have a signal which is in the form of a ramp function. Let us try to write that signal in the form in mathematical expression. So we have a signal x of t So yeah, this is the signal x of t, and we need to write it down mathematically. Let's try to write it down mathematically. We know that the signal starts from t is equal to -1, that it is a shifted ramp function. And the slope of that ramp function, of this particular ramp function, you can see is 5. The slope is 5. So it becomes 5 of r t plus 1. It's a shifted ramp function with slope 5. So this 5 times r of t plus 1 would be something like this, right? But we need to limit this signal to this, right? So we need to subtract another ramp function from here. We need to subtract another ramp function from this total ramp function. The slope is again 5 and it starts at time t is equal to 0. So we'll subtract another ramp function, right? So if after subtraction it becomes something like this. Alright. Now further, if you look at the desired signal at t is equal to plus 5, there's again a ramp function with a negative slope. So suppose this is plus 5 point. So we need to bring down this ramp function to a negative slope. At this point the slope is 1. We need to bring down that slope to negative slope, right? So what we'll do, we'll again subtract another ramp function with slope 5 and shift it to time t is equal to plus 5. So this results into this function. Further, if you look at the desired signal, it should be limited at 0.6. It should be stopped at 0.6, which is here. But till this according to this mathematical equation so far, it extends towards till minus infinity. So further we'll subtract a signal with negative slope here, right? So subtract a signal with negative slope and which is shifted to t is equal to 6. So this is the mathematical expression of the signal. Moving on, the next important classification of the signal is energy signal and power signal. Okay, so first of all, let us see what is the mathematical expression of energy and power of a signal. So energy of any signal x of t can be written as integration of modulus of xt square dt. This is for a continuous time signal, and similarly the energy of a discrete time signal can be written as, instead of integration sign we'll use as summation because we are dealing with the discrete values over there, x of n square. This is the energy of a discrete time signal. Similarly, the power of a continuous time signal can be represented as limit time t tending towards infinity 1 upon t integration minus t by 2 to t by 2 modulus of dt. This is for a continuous time signal. So we can clearly correlate between the energy and power of a signal. It is nothing but the time average of the energy. Power is nothing but the time average of the energy. Similarly, the power of the discrete time signal is limit n tending towards infinity 1 upon 2n plus 1 summation n tending towards minus n2 plus n modulus of x of n square. This is for discrete time signal, power for a discrete time signal. Now let us categorize the signals as energy signal and power signal. What are the important parameters that should be fulfilled? So for an energy signal, energy of the signal should be finite, that is Ex should lie between 0 to infinity, it should be a finite energy, and the power should be equal to 0. Such a signal with energy finite and 0 power is known as energy signal, and on the other hand, power signal, in case of power signal, the power is finite and the energy is infinite. Okay. Another important point to be noted over here is a signal cannot be both energy signal and power signal simultaneously. A signal cannot be an energy and power signal both. And on the other hand, there are some signals which are neither energy nor power signal. There are some signals which are neither energy nor power. And further, all the practical signals have finite energy and are therefore energy signals. All the practical signals. Have finite energy and therefore are energy signals. It is impossible to generate a true power signal. Ideally, it is impossible to generate a true power signal in practice because such a signal has infinite duration and infinite energy, which is not practically possible. Further, all the finite periodic signals are power signals. All the finite periodic signals are power signals. This is a very important point over here, and its vice versa is not true. That means all the power signals are not periodic. Its vice versa is not true. Okay, so based on the above concept of energy and power signal, try to attempt this question where you need to determine whether the given following signals are energy or the power signals. Try to attempt these 5 questions in which you have to find out the energy and power of all the individual signals. That will help you determine whether the signal is an energy signal or a power signal. So please attempt these 5 questions. Further, we'll discuss about even and odd signals. Any arbitrary signal x of t can be written as combination of an even and an odd signal. Any signal x of t is a combination of even and the odd signal. This is the even component, this is the odd component. Basically, an odd signal is a signal where x of minus t is equal to minus of x of t. This signifies a signal. And in case of even signal x of minus t is equal to x of t, this gives us even signal. Odd signal, the way to identify even and odd signal through the graph and the plots are that even signal are symmetric around the y-axis, and the odd signals are symmetric around the origin. For example, cos of t. Look at the plot of the cos of t function. It's an even signal and clearly it is symmetric around the y-axis. And similarly, if you look at the sin t function, if you look at the plot of sin t function, it is symmetric around the origin. Further, the expression of even and the odd components can be written as the even component x of xt can be written as x of t plus x of minus t divided by 2. Similarly, the odd component of xt can be written as x of t minus x of minus t divided by 2. So this was all about the signals, the basic properties, some of the frequently encountered signals. In the coming lectures, we'll deal with the different types of systems, properties of systems, and so on.